Hello and welcome. This is the first section in Chapter 2. And in Chapter 2, we get to a mathematical discussion of one-dimensional motion, building up on the conceptual things we did in Chapter 1. You'll find in this textbook that this is common, where they have one chapter, kind of a qualitative chapter, and the next one is the more mathematics-based, kind of separate the concepts from the problems. And so this is the problems type chapter. This is what might expect from a physics chapter. So what are some key things we're going to be covering in this chapter, although this video is just the first section? All right, what is kinematics? It's a mathematical description of motion, and we're only doing a straight line. We could do horizontal lines, we could do vertical lines, we could do inclines, we could do different combinations of them, but no two-dimensional motion. And so you see here in this figure a complete motion diagram of an object that appears to be speeding up, although it does not have a coordinate system. The role that graphs play in kinematics is essential. This is a critical skill that folks need to know to display information about motion, because what you'll see is that position versus time graphs and velocity versus time graphs have precise relationships. And similarly, velocity versus time graphs and acceleration graphs have actually the identical similar relationship. We will assume that you have had some basic integration and can do basic differentiation. There's a little bit of review in this chapter, but for the most part, we're going to assume that that's been done. And we'll continue with models, trying to think logically about how you model a situation. Again, in most of these problems, the modeling step will be pretty straightforward, so much that you may not even think about it when you're trying to solve it. But down the road, deciding how to model a problem can be very complicated. And then an important application of free fall. This is the first big physical application of kinematics. And how will you use kinematics? These equations show up several times throughout the book. They definitely show up when we do forces. They will show up again when we do energy. Also a little bit when we do gravity. And even when we get to physics 2, when you talk about electricity, these equations still play a role. Okay, so the first section is all about uniform motion. We want to, have a graph of position versus time where the coordinates or the data points more or less make a straight line of some slope, and we call this motion uniform motion. So we have a position versus time graph that is a constant sloped linear graph. And this is our first model. What would be some examples of uniform motion? Well, a person walking down the street, a car going at 40 miles per hour on the road. When you think about a car moving, right? When you've been in a car, there's bumps and you have to speed up and slow down, and all these things. But by and large, those little, like the little bumps and the little curves, when you're changing lanes or something, we ignore all of that. That's what makes it part of a modeling process. When you're thinking about, when you're doing a problem about a car going at 40 miles an hour on the road, don't think that we're trying to include all these little bumps and microscopic jolts left and right. Okay? This is just the simplest motion. It's as if it's just a block sliding on like a greased surface. Okay, so what is, well, we define the average velocity as delta x over delta t. And that is, well, that's really the definition of it. But when we get to the equation, when we get to the equation, we get that we have S final equals S initial plus V sub S delta t. A note about these subscripts, you'll notice that we have the average. They have delta x or delta t or delta y over delta t. We're going to say that that's the slope of the position versus time graph. So that actually makes if you go back to the previous slide, that actually makes a potential velocity versus time graph that we could draw directly under it, right? Because a velocity versus time graph would just be a straight horizontal line. And the slope of that horizontal line the value of that horizontal line in a graph below this would be the slope of the line in this graph that you see here. And so we have an example of relating a velocity graph to a position graph. What would this velocity graph look like when we have motion what does it look like in the x direction in meters, time is in seconds, and we have three different lines. And so as you can see from this picture, you have to find the slope. Now they just give you the slope right here. One thing that I've seen a lot when I grade papers is that to find the slope of the line, for instance, the slope of the first line is pretty straightforward because people remember that it's rise over run. And since the first point is 0, 0, then they often want to say it's -4 over 2. And so you get the slope of -2. Well, first of all, the slope is a physical quantity because it has units. The units of the slope are meters per second. The units of the slope are always the units of the vertical divided by the units of the horizontal. Most people can also reasonably expect that the slope of this mid part is 0, so the velocity is 0. One place where people get tripped up is trying to find the slope of this third spot. And this is where you're confronted with what a slope actually is. Okay? Is a slope the ratio of the values at a specific point on the graph, or is it a ratio of differences between points on a graph? I've had students in later classes that miss points because for this slope here, they might just try they might just try like 6 over 6 or something instead of taking differences between 2 points, right? We know all this from algebra when we first learned about linear functions, but it's easy to forget because oftentimes we're so used to lines that start off at the coordinate 0, 0. So just keep in mind when you're finding slopes like that, because calculating slopes of graphs, not necessarily position versus time, but different types of graphs is always something that we're going to be doing. And sure enough, here we see a graph of velocity versus time. Notice that this is where some calculus kicks in. Notice that at 2 seconds and 4 seconds, there is a discontinuous jump. Okay, so this function, the velocity function, the velocity versus time function, is allowed to have discontinuities when you have instantaneous changes in the uniform motion. What does instantaneous mean? Well, physically, it means that the motion changes too quickly for us to really measure an acceleration. I'll give you an example. Say you are trying to find your position versus time graph for you're driving down like 6 miles of city streets, and there's a stoplight at every mile, at every main road. Well, if it takes about 2.5 or 3 minutes to travel from one city light to the next city light, it only takes maybe 4 or 5 seconds to reach that cruising speed. And so if you were to graph your velocity versus time over those several minutes where you're going from, say, campus all the way to the east side of town, those discontinuities would be where you go from, say, rest to your cruising speed, or rest, or maybe you make a U-turn. Those would be those types of things. So the velocity graph has a discontinuity in it, which means that the position graph has these kinks. Notice these. What do I mean by kinks? I mean that the slope of the graph is not defined at 2 seconds. At 2 seconds. The slope of the graph is not defined at 4 seconds. And why is the slope not defined? Well, the slope doesn't approach the same value from either side. It approaches 0 from the left and -2, or sorry, it approaches -2 from the left and 0 from the right at x equals 2 seconds. And so the limit doesn't exist. That's a calculus technique. Okay. So these are how these graphs go. Just for these position versus time and velocity versus time graphs, we're not complicating it with acceleration just yet. And they also set up the model and do the assessment step. Okay, so a summary of interpreting these graphs, right? The first thing, right, the slope, right, steeper slopes correspond to faster speeds, slower slopes correspond to slower speeds, right? Negative slopes correspond to negative velocities, and hence motion to the left or down. Right? The slope is ratio of intervals, not necessarily values of position versus time, right? That's making the mistake that it's just using the origin, right? And that's the remark that they make at the second line of point 3. Okay, so now what are the mathematics of uniform motion? Because that was the intro. This is how we transition from the pictorial representation to the mathematical representation. Remember, there's all these representations of the problem. There's the verbal, there's the pictorial, now there's the mathematical. So how this works is that when you decide to model an object as uniform motion, based on the symbols that you define, you instantly have this equation at the bottom. And again, this is where it shows up because we have an S. Well, what do we use S for? S is our generic placeholder axis. S could mean x-axis, could mean y-axis, or it could mean some axis along an incline. So with the book, when you look up these equations in the book will have them as S and not x or y. Additionally, and you also see there's an S subscript over the velocity. A note about notation in this book is that vectors, subscripts, or quantities that have subscripts are vector quantities. Quantities without subscripts are scalars in this chapter. And also you notice that there's an initial and final at that equation, right? I would recommend you do zeros and ones in the subscript, or possibly even zeros and ones and twos if you have more than one characterization of motion. But so this is a key feature of your problem solving. Once you identify that the model is uniform motion, you instantly know that for that period of time in which the motion is uniform, this is the equation that you're going to be using. And we have another model box. It summarizes all these things in very good detail. It's got the velocity versus time graph, and it's got a position versus time graph. I would actually recommend that these be flipped, that the position goes at the top and the velocity on the bottom, because you often see that derivative relationship when you're talking about position and velocity. But of course, we have only a single equation. We only have a single equation for the motion. The motion diagram, there's no acceleration in it. We know that the velocity is constant, delta S over delta T, and then we have that S of S equals F final plus, or S initial plus V sub S delta T. What are some limitations of this model? Model fails if the particle has any acceleration, a significant change in speed or direction. If you try to do this for the problem of, say, someone on a Ferris wheel, then you'll get the wrong answer because the velocity is not constant in that case. Speed is, but the velocity isn't. We'll find a way around that in chapter 4. Okay, and so this shows up several different places, but sometimes you just need to have a formal introduction of scalars and vectors. You may have done this already in like a calculus 2 class, but scalars are quantities that only have an amount associated with them. That amount could be negative, but scalars can be further subdivided into strictly positive scalars, and scalars that can be either positive or negative. For instance, well, speed is a non-negative scalar, mass is a non-negative scalar, time interval, provided that you're going from past to future. But scalars can also be negative. I mean, you can have a negative temperature, right, in the right temperature scale. You can have a negative energy. That's another example of a scalar. What about vectors? Vectors include scalars, but they also have a direction associated with them. So vectors, the amount of the vector is a scalar quantity, but they also have an additional information about their direction. So you're driving 40 miles an hour. That's a scalar. You're driving 40 miles an hour east. That's a vector. That extra piece of information about the direction is what helps us to treat the object as a vector. And those quantities in that equation for mathematics of uniform motion are vectors, besides the time interval. So displacement is a vector quantity. Object speed is a scalar. Velocity is a vector. And that's a quick check question. We're not going to be, you could certainly pause this and try it for yourself. We won't be doing these quick check questions in these general lectures. That concludes this first section on chapter 1. In the next section, we'll do a little bit of calculus review, introduce instantaneous velocity, and keep moving forward to how we interpret information graphically. So as usual, thanks for watching, and we'll see you on the next video. Take care.